Thank you, Adrian. Hi, everybody. You will hear me mostly talking about stuff beyond general relativity and quasi-normal modes. That's usually the topics I'm interested in. Not only quasi-normal modes, but the focus of the talk today is gathering some works I've done in the last couple of years with all this bunch of people. Okay, so just an introduction. I don't know how familiar you are with black hole bring down. Why this is interesting for observational purposes, because with gravitational waves, bring down is describing the last stage of the black hole binary merger. The cool thing is, like, theoretically it's described by black hole perturbation theory, and due to its simplicity, it's a very good test of general relativity. So basically, it's the last part when the two black holes merge, then they relax to some stable configuration, and this relaxation is like throwing energy through gravitational waves, and these gravitational waves have a very characteristic damped sinusoid signal. So more focusing on the mathematical structure of the ring down, we usually see it as a superposition of damped sinusoids, as I said. So basically, the key part is encoded in this term, the quasi-normal mode frequencies, which are complex, but for according to general relativity, they're determined just by the mass and the spin of the black hole. So now I want to just revise quickly on how the computation of quasi-normal modes is done in general relativity, and then from this will be the starting point to see how we can extend the calculation beyond general relativity. So in GR, the idea is to take background metric and add some perturbation, considering this epsilon small parameter, and plugging in into, I don't know, computation of invariance of our metric. So for example, there is a scalar, so on and so forth. Basic assumptions like we are in vacuum, spherical symmetry, so like fluxed metric for our background. And then from this, we can compute the Einstein equations at first order in the computation. And usually in spherical symmetry, it's a clever thing to split the metric into perturbation that transform nicely on the parity transformation. So there will be polar perturbations and axial perturbations. This is like how they transform after transformation of the angles of our the spherical coordinates. And after, so this is like usually what is taken as the Regge-Wheeler gauge. Of course, you can study perturbations in whatever gauge you want, but the most convenient way to derive the calculations. So this is the answers for the polar part. This is the answers for the axial part. So the idea is like you put these answers into the Einstein equation, you do some machinery with the equations, and after combining them properly, you end up with two separate equations, one for the axial perturbations and one for the polar perturbations. But both of them can be recast in this Schwarzschild-like form. The only thing that's changing is the effective potential of the perturbations. So this was a very old works. The axial one was done by William in 1957. Polar one had to wait a few years, but then Zahili in 1970 found it. Okay, this is cool. When we add rotation, stuff is a little bit more complicated because there is no direct way to do it through perturbations of the metric. So in 1972, Teukolsky found this cool way of using the Newman-Kerners with the decomposition of the space-time. If you've never heard of it, just projecting the curvature invariance on a tetrad that has some properties. And again, after like a lot of maths, Teukolsky managed to split the problem of perturbations for Kerr into two separate equations, one for the angular side and one for the radial one. And the difference with the spherical symmetric case is that the potential for the radial equation now is complex and it's long range. And then, of course, because of the rotation, there is a degeneracy breaking in the azimuthal number. But again, at the end of the day, the frequencies that are computed with this formalism just depend on the mass of the black hole and on its spin. So in general, the equation will take, as I said, this form, and it's important to set up the right boundary conditions if we want the quasi-normal problem. So we want a purely outgoing way at infinity and purely ingoing on the horizon. And then by setting up this eigenvalue problem, the eigenvalues that you find are an infinite number, and usually we'll label them by these three numbers. The first one is the Overton number. This is just an ordering of the decay time of the mode. The higher the Overton number, the faster the decay time. And then the other two, they correspond to the angular modes. So there is the angular momentum and the azimuthal momentum. So more or less, this is what is needed to know on, like, roughly what is the calculation of quasi-normal modes in general relativity. What is happening beyond GR? So beyond GR, there is a huge zoo of stuff you can find. In this talk, I will focus on a specific case, but let's first of all look at what could be the causes of deviations. So first of all, beyond GR, we might have a different background metric. So this will affect the final equation because the metric is different. But then, of course, there is also different dynamics. The equations of motions are different. So these two elements combined, they will give rise to a different equation for the perturbation, for sure. Okay. But then on top of this, in alternative theories, there might also be new fields and new fields coupling to gravity. So this might create coupled perturbation equations. I'm thinking in cases where, like, there is a scalar field coupled to gravity. In that case, there would be a system of two perturbation equations. Do you have a question, Dave? Okay. And also bear in mind that there might be cases in which the boundary conditions are modified. For example, if there is some hard surface, like black hole mimickers, stuff like that, the whole picture I described before is, of course, changed. And the difficulties, because so far the number of quasi-normal modes in alternative theories that have been computed is very limited compared to the ones in general relativity. And here I'm listing some of the difficulties that are around. So first of all, yeah, maybe the quasi-normal modes have been computed, but only in spherical symmetry or for slowly rotating black holes, but not for fully rotating ones. And then there might be problems of the, so, as I said, the Teukolsky managed to split for the rotating case radial and angular equation, but this is due to a very nice property of general relativity of Kerr black holes. But already in the case of Kerr-Newman, you cannot separate the two equations. So you need to resolve to some specific numerical methods to solve the equations. Another case is, like, sometimes you cannot even recast your equations in the Schrödinger-like form, so like Reggie Wheeler and Zerilli. So you have a system of coupled equations, so you cannot use the same methods you had for the general relativity. And usually overtones, so the faster decaying quasi-normal modes are very hard to catch, and already in GR, but beyond GR even more. And sometimes it's not even clear how to set up boundary conditions. I don't know, for the case of Lorentz violating gravity, where you have black holes with multiple horizons. So, like, it's very hard to define a perturbation problem where you have coupled modes, but they see different horizons. So stuff like that is like a list of reasons why the computation of QNMs in alternative theories of gravity has been much slower than in general relativity. In this talk, I want to forget about boundary condition problems, so focus on the first 4 cases. So in the last 2-3 years, maybe 5, there has been a huge advance in tackling all of these problems. So I want to talk about this. So there are in general two strategies that are very convenient by making some assumptions on our theory beyond general relativity. So the first assumption that usually has been done is assuming that the theory has an action of this form. So it will be general relativity plus, in case, some additional fields. This is not necessary, but if they are there, they have their own dynamics. And then some interaction term that couples those additional fields to general relativity, or metric terms coupled in a non-GR way between themselves. And there are, and the key assumption is that the coupling term is taken to be very small in some units. And there are many examples in the literature that can fit this definition. For example, scalar tensor theories, higher derivative gravity, Einstein scalar gas-Bonnet, dynamical Chern-Simons, Einstein-Maxwell, and you can think of your favorite theory if it can fit these, then maybe some of the things that we talk about can be up. And the other overall assumption to simplify the calculation is to perform an expansion in the spin of the background metric. So overall, you can think that your background metric is described by the Kerr metric plus some corrections in the spin and in the coupling, perturbative corrections. And in this way, we solve one of the biggest problems of the computation of quasi-normal modes beyond GR is that in most cases, the metric is not known analytically, but at least performing this double expansion in the spin and in the coupling, we can have corrections that are analytic in the functions of R and theta. Okay, so the idea is to perform a simultaneous expansion of the perturbation equations, both in the spin and in the coupling. And you can think of this problem in going in two directions. Either you keep the spin expansion low, and you can increase the order of the coupling expansion as much as you want. So taking, like here I call N and M, the expansion for the spin and for the coupling. So usually what has been done in the literature is keeping N up to 2, so expansion in the spin up to quadratic order, and taking M as large as possible. Or the other approach is the opposite. Take a lower order in the coupling expansion. So usually in the literature, this is what has been achieved. And then take as higher as possible for the spin expansion. And doing high in both directions so far is not possible because of computational difficulties. So this is what studies available now are limited. Bear in mind that this is not the only way to find solution for the quasi-normal mode problem. There are in the last year also propositions to solve the problem fully numerically, so without the necessity of having analytic background metric. But I think this is necessary to compare the goodness of the results. So now I want to explain how the core perturbation is done in slow rotation. So if you remember before, this can also be applied to pure GR. So if you remember before, we take a metric, we perturb it, we plug it into the Einstein equations, we perturb them, and then we look at what is there. So now we assume vacuum, but with slow rotation. So it's the Schwarzschild metric plus first and second order correction in the spin, which can be taken by taking the slow spin limit of the Kerr metric. And plugging it into the Einstein equations and doing the same steps done for the Reggie-Wheeler and the Zerilli equation gives rise to two Reggie-Wheeler and Zerilli-like equations, but with correction in the potential. So there will be a first order and second order in the spin correction to both potentials, assuming also a correction in the tortoise form that is defined here. Okay. What is cool in general relativity is something I found a couple of years ago, is that in the 70s, Chandrasekhar managed to find a relation between the Reggie-Wheeler and the Zerilli potential, because in general relativity, these two potentials have the very cool property of being isospectral. it means that even though they're very different from each other, the whole spectrum of frequencies, of infinite frequencies, is exactly the same. And this is because there is a transformation that can bring one equation to the other and vice versa. And even more interestingly, this relation holds. I mean, this is expected, but this is what I showed in this paper in 2023, is that this transformation can be generalized at least up to second order in the spin. I didn't check at higher orders. But it's just a nice confirmation that this spectrality is holding higher orders. And even more interestingly, Chandrasekhar also found a transformation that can bring the Regge-Wheeler or the Zeril equation into the non-spinning Teukolsky equation. And of course, this transformation also is valid up to second order in the spin. So it's like kind of closing the whole picture.
So what do you mean by non-spinning Teukolsky equation?
So you take the Teukolsky equation and you put A to 0.
Okay. But then it's valid up to second order.
Yeah. So this transformation with A equals to 0 was found by Chandrasekhar in 1975. Because Chandrasekhar was not interested in slow rotation.
Okay.
And then, yeah, what I found 2 years ago is that this transformation can be generalized at least up to second order in the spin.
Okay.
And my guess is like it should exist at any order in the spin, but it has not been proven yet because we don't have an equivalent of the Regge-Wheeler and the Zeril equation at any order in the spin. Okay, now we know all these things about slow rotation. So how do we do it beyond general relativity? As I said, the background now will be a double expansion in the spin and in the coupling of these nice analytic equations. Then you plug everything into the equations of motions that now will be modified by some stress energy tensor of any additional field. And then assuming that the spin and the coupling constant is null, and by performing the same combination of equations, you can get a new set of perturbation equations. Now there might be coupling between the gravitational fields and additional fields. And of course, the effective potential will contain corrections in the coupling. Okay, so just to briefly conclude this section, the status right now in the literature for specific theories is the following. So for higher derivative gravity, which I will cover more later in this talk, there has been computed this equation at first order in the spin and first order in the coupling. And then for dynamical Chern-Simons, if you're interested in these theories, I can tell you what they look like. But in the end, these two, they introduce a scalar field that is coupled to gravity, to quadratic invariance of gravity. But for the sake of the information, it's just not necessary to see how it looks like. But again, so for dynamical Chern-Simons, its calculations are done first order in the spin and first order in the coupling. And scalar Gauss-Bonnet is the one which has been pushed more. It's up to second order in the spin and sixth order in the coupling. And so it is clear here that, as I was saying before, Chandrasekhar explained why there is isospectrality in general relativity. But of course, the introduction of this additional term is breaking isospectrality. So this can be one of the smoking guns of beyond GR effects. Now, how is perturbation theory performed in the small coupling limit? So forget about what I said until now. It's the other direction of the expansion. So this can be performed with full Teukolsky. So at least the background GR part is computed at any order in the spin. So it has the advantage of being able to cover quasi-normal modes for highly spinning black holes. But the idea is the following. You take the Teukolsky operator, and then you compute what are the corrections at first order in the coupling to this operator. the thing, like if you're familiar with the Teukolsky formalism, there will be some terms here that will be proportional to the perturbations of the metric. But then there is the so-called metric reconstruction, which can bring you the perturbations of the metric into perturbations of the scalars, which are the actual functions that the Teukolsky operator is working on. So in the end, you will have an equation that is just applied to the scalars. But this reason is the main limitation to this formalism, and is the reason why it's highly non-trivial to go at higher order in the coupling, because at higher order in the couplings you would need to do metric reconstruction, but including non-GR terms, and this nobody knows how to do it. So we said before that the Teukolsky equation depends on just the black hole mass and black hole spin, and of course the spin of the perturbation, so like tensor perturbations. But now, because of the new term, there will be other quantities. So the Noether theorem is broken. A little bit more into detail. The idea now is to take the following answers for the perturbation, and in general, this term here will not decouple the radial and the angular part. But there are ways that people have figured out by assuming that zeta, the coupling parameter, is small, to be able to decouple this equation. So if you recast the equation into this form and expand everything into spheroidal harmonic basis, which is the basis of the perturbation of the Teukolsky formalism, you can then use the fact that the spheroidal harmonic are a basis, and it's a complete basis. So you can project all the equation onto a selected mode in the angular part, use the completeness, and all the residual terms that you would have coupling, they all enter at higher order in zeta. But here we are truncating at first order in zeta. So in the end, only these terms here survive. Meaning that with the assumption of zeta being small, it is actually possible to decouple between the radial and the angular equation. So this has been done for a few theories. So for higher derivative gravity, calculations have been performed at first order in the coupling, as I said, is the main limitation, and 18th order in the spin. And this 18th order is mostly for the computation of the background metric. And it's so high because it's needed to reach the highest possible value of the spin, so that you can have predictions of quasi-normal modes around 0.7, which is what is relevant for observations, because we know that black holes forming from binaries spin around with a spin around 0.7. Dynamical Chern-Simons, because of the coupling between tensor and scalar perturbations, way more complicated. So far it's only been performed the first order in the coupling and first order in the spin, and only the equations of motion, they haven't even solved them. And for scalar Gauss-Bonnet, nothing has been done. And now I will talk you what we did for the agnostic modeling. So without assuming any theory in the background, but trying to be as generic as possible. So these two cases is what I'm going to talk about next. So let's see in detail. The radial Teukolsky equation in GR looks like this. So it's second order equation in this function, eigenfunction, that is coming after the separation of the two equations with some effective potential. And what is happening beyond GR, because we know from, at least from the case of higher derivative gravity, is that the only difference with the Teukolsky equation is an additional term in the effective potential. Of course, this correction depends on the theory, but here we want to be agnostic. So we try to describe this term just with a radial basis. So we take this agnostic modification, so a sum of terms, of radial terms with some power k, that go from some very small, like large but negative value. So like terms in 1/r to some power up to r equals 4. And you might wonder why is 4, because this is the last term that maintains the potential not exploding at infinity. So this is the last term at which, if you look at the effective potential, because now by the way it is written, it's not obvious, but yeah, here there is this delta, and then there might be transformation. So it's the highest order that appears in this potential here as well. So we want to keep it consistent. Yes.
If it was a higher derivative, what happens in a higher derivative?
Yeah, we'll show you next. So now I'm showing the agnostic case, but higher derivative gravity, there are only some of these alpha k being non-zero. So if I remember well, there is k equal 2, 1, 0, and -2 that are non-zero, and all the others vanish. So the correction for higher derivative gravity exactly looks like this, but only for some selected coefficients.
Why do you get higher derivatives to the function of R?
No, but so higher derivative gravity, yeah, let's go forward. It's what this theory is called. So it's a theory where you have GR, and then you have a new term in your action that is taking like higher powers of the curvature. So this is one of these theories. I think we computed 5 different ones, but they have terms of this kind. But because of the smallness of the coefficient, like all the bad terms go away. Yeah, we are always working in the regime of, so we are considering this as an effective field theory. And so you always have to be in the regime where the coupling is small and the theory looks like GR. There might be other branches, but we are not interested in the other branches of the theory. So this is why sorry, yeah.
The perturbation on the potential doesn't, so it depends on the theory, but it depends also on the angular part, the radial equation.
Yeah, okay. I'm not showing it here. We also considered because the radial equation, because of what I was saying here, we are assuming that is in spheroidal harmonics. So we are assuming to expand the angular part always in spheroidal harmonics. So the equation is the same. The only difference is the separation constant, because separation constant depends on the frequency. So if the frequency is shifted, then also the separation constant is shifted. So we took this into account. Now I'm not showing it in the slides because of simplicity, but in the full derivation of the problem, we are also considering that. But yeah, the assumption is that all the modifications are appearing only in the radial equation. And then the angular part is inheriting then because of the shifts in the frequency. And yeah, okay, the overall assumption, then I will get back on this later, is that all of these coefficients are somehow proportional to our coupling constant. So they are small. So the idea is like, if we have this equation and these corrections are small, then we will induce some small corrections to the frequencies and to the separation constants as well. So the shifts to the quasi-normal modes of Kerr will be now corrected, at least at the linear level, with some part that is theory specific. And then these coefficients, they do not depend on the theory. They're just the Taylor expansion of the computation of quasi-normal modes. So they are universal. So once you fix your mode numbers and the spin of the perturbation, you can compute them and store them in a file, so that once you pick up your favorite theory, or if you want to do analysis of bringing down agnostically, you can just choose what are the values of alpha k and have automatically the frequency given you. So in this paper, we computed all coefficients spanning from n equals 0 to n equals 2, from L equals 2 to L equals 4, all the possible m's for k going from 4 to minus 3. And here in the plot, you can see the imaginary part versus the real part of the coefficients for all the coefficients for the fundamental mode and n equals 2, and different colors refer to different azimuthal modes. And you know that for spin equals 0, the azimuthal modes coincide. So the non-spinning case is given by this black dots. And here is it's an inset zooming on this part of the plot. And then for different k values, k is the power of the exponent, you have this branching from the non-spinning value to increasing values of the spin. So this is computed up to spin a equals 0.95, I think. I don't remember. And all these results are available in this GitHub, and there is also a tutorial on how to download them, how to blah, blah, blah. So if you're interested to play with them, you can find them. I was saying before about the smallness of the coefficients. So here, as I said, we cannot go to next to leading order in the correction of the Teukolsky equation because of the limitation of the construction of the formalism. But at least we can compare the solution of quasi-normal modes of this equation, assuming the linear expansion, so what you find here, or you can fully non-linearly compute the quasi-normal modes. And this is at least giving you an upper bound of what is the regime of validity of this thing. So when even the linear regime is exceeding more than 1%, more than 10%, whatever you want, the non-linear one, then you know for sure it's breaking. Then for the theory you don't know, but this is what we could do.
Before we go there, can you
Yes.
go back to the plot?
Yes.
So some modes they have a negative imaginary part.
And this is not the imaginary part. This is the D. And you also always have to remember that these coefficients are first of all multiplied by alpha.
Okay.
Alpha is small,
You have to add
and then there is a sum over k. So whatever you see here is not telling you much about the final frequency.
How do you know for sure that series for the frequency will be the old frequency plus that series and the old series?
You hope for that. We don't know. No, okay. Heuristically, we know that this expansion, so the way it's written maybe is not very clear, but it's going r to the fourth term, then r to 3, r to r square, r1, 1 over r, 1 over r squared, and so on and so forth. So it's like a post-Newtonian like expansion. And you know that this is modifying your potential closer and closer to the peak. So I don't know. There is no way to say if it's converging or not. What you can see from the plot is that at least for small values of the spin, for higher values it's not, but the coefficients are getting smaller and smaller. I know it's all heuristic. We couldn't prove it because in the end, all this stuff is numerical. But I don't know. It seems to work. We applied it to some known cases. So, for example, massive scalar perturbation on Teukolsky, and it was giving the right results. We were trying it on the Kerr-Newman, assuming the charge being small, was giving good results. Of course, these are like theory specific, so they're not taking all the terms. I have no idea, but I see this formalism rather than like a fully theoretical work, more like a interactive tool to simplify the computation of quasi-normal modes for given theory and to give some inspiration on how to do data analysis in a more informed way on how deviations from GR could be. But at the end of the day, you would always truncate this series at some point, and I don't want to be formal in doing this. I want to be useful.
It's the right expectation, as long as these additional terms in the potential don't have the derivative, you know?
Yeah.
So,
Yeah. Also, I mean, bear in mind that the terms one over R, they're always like shielded at the horizon, so they will never grow too much, I think. I don't know. You can look at it. I didn't. And also, yeah, there is one additional thing that you can always perform field redefinition and kill some of the terms. So actually, the only terms that matter are up to, I think, 1 over R squared. So you can always do that, assuming that the constants are small, and you just redefine, yeah, your field and your yeah, the field itself, and you can always eat back some of the coefficients. So in the end, I don't know. I'm not too worried, but we can discuss about it.
I guess one more question.
Sure.
In the plot, what varies along the lines? Sorry,
Along the lines is the spin. So the black point is non-spinning, and then as you increase the spin, you get farther and farther from this point. So the last point, I think it's 0.9 or 0.95. I don't remember. And then steps are 0.05. So each point in the plot is taking some steps. Okay. Okay, so as I was saying, we want to just have an estimate on when we should stop to use the linear calculation. So we apply the full lever calculation to the potential. If you don't know, lever is a continued fraction method to compute precisely quasi-normal modes of equations, and we found the parameter space of the spin and the coupling, and setting, I don't know, I think it was 1% limit of, for a given spin, what is the coupling at which this relative difference saturates at 1%. And this is the plot that summarizes this result. So for a given perturbation, so for example, k equals 4, you see these are the purple dots. You have the value of positive and negative alpha, at which the linear minus nonlinear relative difference of the frequency is at 1% for different values of this. So this is just telling you that all the, let's say you choose the spin 0.2, here the spin is normalized, the mass is normalized in 1 alpha. That's why extremality is 0.5. So let's say you take spin 0.2. This is the maximum negative value you can take for alpha 4 to have the relative difference at 1%. So if you take larger in magnitude value, the difference will be larger. If you take smaller, the difference will be smaller, and so on and so forth for all the different values of k. So this is at least telling you if you're taking a larger value of alpha, you're going for sure outside the region of validity of the linear expansion. Okay, and now we apply all of this to specific theory. I don't know if you have more questions. Okay.
So in this plot,
Yes.
what exactly is computed from the non?
So it's the computation of omega. So it's omega linear. I mean, we should have put there minus omega non-linear. Omega linear, absolute value. And the omega non-linear is computed by employing the Lever method to the equation. So it is possible to generalize.
Whatever your linearized field equations, and then you plug in.
Yeah.
You plug in the ansatz and do the full technology.
Exactly. To compute the quasi-normal, you have an equation and you solve the boundary value problem. Instead of assuming that this correction is small and having a quick recipe for the QNMs, you just say, okay, I don't know about this. I compute the QNMs all the way. Just it takes longer. That's why it's not convenient when you have so many different possibilities. Okay, so higher degree gravity. Now I'm showing you only one of them with 5 different ones, but they all, as I said, include corrections to the Einstein interaction, including couplings between the Riemann tensors, cube or particle. There is a huge amount of calculations to get manipulations into the modified Teukolsky equation, but in the end, if you remember the formula I showed you before, you can show that the only relevant terms in the modified potential only contain these 4 non-zero alphas. So overall, you can just apply the linearized computation for the QNMs to find the shifts in the frequencies. That's just a sum of the, okay, this is badly written. This should be alpha k times dk. And for the people who are interested, all of this calculation has been performed up to the 18th order in spin, and performing a resummation in spin a la Padet in order to achieve the highest possible values of the spin for the frequencies. And this is what the frequencies look like. And it's for the first time that an accurate computation of beyond-GR quasi-normal modes. So as I said, we did it for fundamental and first 2 overtones, for angular momentum from 0 to 4, all the possible m's, and spin depending on the mode up to 0.7 or even 0.9. And this stuff is ready to test against data. It was actually being done. I didn't put the reference in a paper that came out in November or December. But yeah, in this plot, you can see the prediction of the real and imaginary part of the. So this is L equals to NEM fundamental mode. And there is, because of the breaking of spectrality, there will be polar and axial modes. So there is the splitting that in GR normally does not appear, but here we have it. And as you can see, there are the points are the computed QNMs, and the lines, if I remember well, they are the interpolated values up to the regime of validity and then extrapolated for, sorry, no. It's the interpolation of the expansion at the order before the leading order, so the last leading order, just to see that up to certain point, like for example, take the I don't know, m equals to line, leading order and next to leading order they coincide, and then they start diverging. So this is where we stop the computation after some point, and this is why the maximum value of the spin changes depending on the mode content, because different modes are sensitive in a different way to the rotation parameter. Okay, so these results I think are pretty cool. And I think I said enough stuff. I can conclude here. Just to summarize, this analysis until now was limited only to non-rotating and slowly rotating cases. And for the first time, the beyond-Teukolsky formalism was actually applied to compute quasi-normal modes for fully rotating solutions. And to tackle the problem of non-separability of the equations, we assumed simultaneous mode coupling and slow rotation expansion. I also showed how slow rotation can be used to obtain generalized Regge-Wheeler limitations. And I didn't talk much about the difficulty in computation of overtones, but as I said, quickly, the continued fraction method of Lieber can be used also to these modified systems. So the overall message that I want you to take home is that modified Teukolsky approach is now working in the direction to extend the results to astrophysically relevant case. The next step is to apply to more difficult theories. But just to remember that adding one layer of complexity doesn't make the problem impossible to be solved. It's just like writing a two-layer spike. And thank you for the attention.
So, in the previous slides.
Yes.
You showed that there's something regime of validity. So how do you, what is the definition of the regime of validity?
So we compare the results of the spin expansion at 18th order against those at 16th order. So if the adding of one correction in the spin doesn't change much, then you say, okay, I trust it. When it starts splitting, then you say, okay, maybe I need more orders to get a more precise result. This is.
And so with 16 order, you can go only up to 0.7 for some modes.
Yes.
I need a lot.
Yes.
So again, in these plots, again, the negative imaginary part, it's the same thing in these plots.
Again, now this is delta omega. So delta omega is defined as the full frequency minus the Kerr1 divided by the, so it is the linear correction modulo the coupling. So again, this will be multiplied by lambda, but lambda, you know, it's
So
small.
you cannot, so you can never say that for a certain lambda, for a certain spin, you get an instability.
No, actually, we checked for values of lambda for which the regime is valid. So the same thing I was saying here, but so here this has been done varying one alpha k at the time. So when I say k equals 0, I mean that all the others are 0. But for this case, we switched on all the corrections and compared the nonlinear against the linear and say, okay, what is the maximum value of lambda at which we can trust our results in the linearized case? And for all the parameter space we checked, there is no instability. So at least these values are rather small because we are working at linear order in lambda. But at least, yeah, for the values we checked, there is no instability.
And do you have also the solution for this?
Yes, this is available. Yeah, exactly. Slowly rotating up to 18th order. Yes, it's available. There is a in the paper there is a link to the. Yes. There is a Mathematica file that contains all the solutions. So if you want to use them, you can.
Just a sanity check.
Yes.
The background here, it's already Kerr or is it Schwarzschild?
No, it's Kerr plus corrections.
But imagine doing the following: take the background to be Schwarzschild.
Yes.
And perturb in GR. So set lambda to 0, lambda EB there, the coupling to 0. Perturb, do a small spin expansion around Schwarzschild. In which case you know exactly what you expect to get. Do you?
Yeah.
Completely matching it.
Yeah, we did that. And as I said before, we checked against the massive scalar perturbation, assuming that the mass of the scalar is small, and Kerr-Newman perturbations, assuming the charge is small. So because Kerr-Newman is fully rotating, so you can actually check the regime of validity of the expansion even for large spins, assuming that the charge is small, and it's working very well. And again, because there was a previous paper where they computed the QNMs of this case with direct integration. So it was like, and Simon for this paper, he employed this quantum mechanics variation. I don't remember the details of the computation, but we checked independently that the results are correct and they match. So yeah, we did several checks to see if the expansion works.
If I may propose one more check.
Yes, please.
But it involves a lot of work again. So in 5 dimensions, there's an exact solution in Gauss-Bonnet gravity.
Okay.
That's fully analytic, no spin.
No spin. Okay.
But you could do the perturbation expansion in the coupling parameter and compare with the exact analytic solution. That's an exact solution.
Yes. Then this can be a good master project, I think.
Just exploring.
No, in the sense that can be interesting. I don't know.
I follow your reason.
No, it can be interesting to check, but I mean, yeah, some work that needs to be done. It's not trivial.
If you enjoyed the video, like and subscribe.